Our goal for today is to look at a couple of what are called measures of dispersion. And this is a way to put a number on how tightly bunched or spread out a data set is around its mean. You might be familiar with something called a normal distribution. So when we do a histogram of a set of data, there's three things that we're looking for. If the highest point, the most frequently occurring item, is on or about the mean, if the data declines on both sides from that high point, as it does here, and is roughly symmetrical, then this is what's known as a normal distribution. It occurs often in nature, and so you probably already studied it in some of your science classes, and if you have Project Lead the Way, you've definitely looked at this, and you'll find out more about it as you move on with some of your statistics classes. If the mean and the median are not the same, then we have what's called a skewed distribution, just showing that as an example. But right now, we're mostly just looking at that standard normal symmetric distribution. So where the mean is our measure of center. And if that's the case, we've got a couple of measures that we're going to look at. One that's called the variance. And you can see from your notes, the definition of variance is the average of the squares of the deviation away from the mean. And this is what that looks like in math notation. We use a lowercase Greek letter sigma, and we show this as sigma squared. We'll find out why squared momentarily. The capital sigma we use in math to represent sum. So x is each individual data item, and we subtract off the mean. We're using the Greek letter mu to stand for mean. So this says that we're going to take each item, subtract the mean, square that so that it becomes positive, add all of those up, and then divide by the number of items. And that will give us a measure that's known as variance. So as an example, we'd like for you to find the variance of the following data set: 79, 98, 68, 94, and 86. So you can see that this is pretty well spread out. I've got a range that goes from 98 at the high end to 68 on the low end, and the average probably should be somewhere in the middle. And when we calculate that, if we add these five numbers, we get 425 and divide by 5, so an average of 85. So the first thing that we'll do under the column that's labeled X sub I, each individual data element is listed. So the 79, 98, 68, 94, and 86. In this table, the next thing that we'll do is list the average, because our plan for the variance is to subtract these two numbers. And that happens in the third column. So 79 minus 85, that's negative 6. 98 minus 85 is 13. 68 minus 85, negative 17. 94 minus 85 gives 9. 86 minus 85 is 1. Now we notice that some of these numbers are negative. So if we add them together, we're going to end up with a sum probably close, somewhere to 0. It's all going to bunch mostly around the mean. And we're really interested in distance. And as we remember from other things that we've done in algebra, distance is always positive. So let's square these values so that they become positive. So negative 6 squared is 36. 13 squared, 169. Negative 17 squared is 289. 9 squared is 81. 1 squared is 1. When we add these five values together, that's our sum of each individual value minus x bar, the average, which we also use mu to stand for, and we get 576. There were 5 elements in our set. So 576 divided by 5 gives us a variance of 115.2. One of the more commonly used measures to talk about how tightly bunched data is around the mean or spread around the mean is standard deviation. And in particular, when you talk about that, the normal distribution, you'll hear reference to standard deviation. And if you take a look at this formula, this piece should look really familiar. That's just the variance, the sum of the data item minus the average squared divided by the number of items. And now we're taking the square root of it. So where in variance this was sigma squared, or standard deviation, we're just going to use sigma to stand for that. So let's do a couple of examples. What I'd like you to do is stop the video and go ahead and fill out the table you find here for the you try number one, the standard deviation of the following set. Your first move is going to be to find the average of those 5 numbers. So go ahead and pause the video, find that average, and enter that into the second column. So the average that you calculated was 10. 8 and 9 is 17, 11 and 12 is 23, that's 40, plus 10 is 50, divided by 5 gives 10. So next, we subtract each data point minus the average. And these are our differences, -2, -1, 0, 1, and 2. We square those, we get these numbers, 4, 1, 0, 1, and 4. So for our variance formula, we add those. 4 and 1 is 5, 1 more is 6, and 4 makes 10. So 10 divided by the number of data points, 5, gives us a variance of 2. So to find the standard deviation, we take the square root of the variance. So our sigma value is the square root of 2, which is about 1.4. And I think that one makes some sense. It's kind of the average distance away from the center point, the average distance from the mean. The mean is 10. Go ahead and repeat that process with the you try number 2, the standard deviation of this data set. And come back and we'll check your work together. So as you calculate the average, you found that the average of this data set was also 10. But you notice that the values are a little more spread out away from the mean. What does that look like when we do these calculations? So here is our data points minus the average. -3, 7 minus 10. 8 minus 10 is -2. 10 minus 10 is 0. 12 minus 10 is 2. And 13 minus 10 is 3. So when we square those, 9, 4, 0, 4, and 9. So taking a look at our variance value, sigma squared, adding these values together, I get 26 divided by 5 gives me 5.2. My standard deviation, the sigma, is going to be the square root of 5.2, which is about 2.28. And as we talked about when we talked measures of central tendency, more so than just calculating the numbers, because let's be honest, Excel can do this way faster than we can, and we'll find out a little bit later that it does. But we want to understand what this difference means, these differences in standard deviation. What does that tell us? And so if we take a look at this next question, compare the means and the standard deviations from both samples and explain the findings. Well, if you take a close look, you see that the average, the mean, in both data sets was exactly the same. But the elements were different. The means were equal, but the elements are more spread out in number 2. 2 away and then 3 away. 2 away and then 3 away. In our first example, was going down by 1, up by 1. So the averages were the same, but the data points in the second sample were more spread out, and thus the variance and the standard deviation are higher than they were in our first example. So go ahead and take a minute and work through example number 2, calculating mean, variance, and standard deviation for the Miller family and the Lopez family. You can check your work here on the video. And then we'll talk about question B in class. And we'll work through the rest of the practice problems in this notes packet in class as well.